Now let's look at how we can solve inequations that have indices in them. Now an inequation is also called an inequality. It's like an equation, but instead of an equal sign, it's got a greater than or less than sign there. Now I've got three different methods for you here. Why three? So that you can pick your favourite, but also so that you can listen and take note of the other two methods that might not be your favourite, and that might build on your understanding of what inequations really are. Now, first method says take the log of both sides, but be careful, because we know that if you multiply or divide by a negative number, you have to flip the sign. Now, you've probably seen this before. If you have something like negative x is less than 3, and you want to find what x is, if you've multiplied or divided this side by a negative, you've got to do the same to this side, but you also have to flip the sign when that happens. So that's a big caution on method 1. Otherwise, it's a great method, you've just got to be careful. Method 2 is, well, if you're worried about making this mistake, you could treat the greater than or less than sign just as an equal sign and solve it. Now, this has the advantage that it's much easier to do the solution part to find what x should be. But at the end, you'll have to actually just use your brain and think about whether x needs to be bigger or smaller than the solution that you've found. Now, this is not necessarily a negative, having to use your brain at the end of the question. After all, it makes sense when you get to the end of a question to think, does that make sense? Does it seem right? And this method forces you to do that, which is actually something you should be doing anyway. So this can be an advantage, it can be quick. Method 3, same as method 2, but to work out whether you need to use a less than or a greater than sign, you're going to make a graph of y equals the left-hand side and y equals the right-hand side to spot your solutions. Now, it won't be a fantastic graph. It won't have any detail to it. It can be a quick mud map, just so that you can think about what the solutions might be and what makes sense. Okay, so I've got an example here. Now, we've already looked at how to solve 2 to the power of x equals 15, but what do we do when it's 2 to the power of x is, say, less than 15? All right, let's follow through. Method 1 says take the log of both sides. So I'm going to start over here, so I've got a bit more board space. So I'm going to take the log of the left-hand side. Now, what should the base be? It should be 10 or e, because that's what we have buttons for in our calculator. We haven't really worked with e yet, so let's use a base of 10 and say we're taking the log of that whole side and we're taking the log of this whole side. Now, taking the log of something might not be something you've done before, but it's an operation that we can perform on both these parts. And because it's the same operation, this statement should still be true. What can we do next? Well, we're looking to get the x by itself. So now we need to use the power law. We know that the x can come floating down the front and land out the front here. So that's my next line of working, is to actually apply the power law and bring it out the front. Okay, now how do I get the x by itself? Well, at the moment it's been multiplied by this number. This is just a number here. It's a complicated number. We don't know what it is without our calculator, but we can, if we can multiply by it, we can divide by it as well. So let's divide both sides by this number. That will leave us with x on its own here. And over here, we will have this whole side divided by that. Now, all we had to do here was be careful. Was this a negative number? Well, the more you do of these, the more experience you'll get with seeing that for this to be negative, you'd need to be taking the log of something like 1 or less. So if this is like 0.9 or a half or something like that, that makes it negative. If you're not sure, just type log 2 into your calculator and see if it's positive or negative. If it's positive, then you don't have to flip the sign, and this is all going very well. Now at this point, we need to put this in our calculator. So we can just type in log of 15 using the log button, L-O-G. So we've got log 15, close bracket, divided by log 2. And we get 3.9. So x has to be less than 3.9, and I've rounded that off to 1 decimal place, so I'd better say so. Now, check that this makes sense. 2 to the power of 4 would be 16, so it makes sense that we need 2 to the power of 3.9 would be 15, and we need it to be smaller, so x needs to be smaller than that. Quite straightforward. Method 1 was pretty easy to do. All right, let's do method 2 over here. Method 2 says, let's just pretend that was an equal sign for now and solve and see what x would be. All right, easier to do the second line here. We can just retell this as a log. 2 to the power of x equals 15. At this point, we can figure out what x is by just using our change of base law, which by now you're hopefully familiar with and don't even need to write out that it's this over this. We can just put it in our calculator. Log of 15 divided by log of 2, and we'll get that same answer, 3.9. Now that step was quicker, but when we get to the end, we have to actually think about what the solution is to the problem that we were asked. We know that now 2 to the power of exactly 3.9, actually it's not exact, we've rounded it off, gives us 15. So if we want a number that's less than 15, obviously we're going to need to raise 2 to a slightly smaller number. So that tells me that x is going to need to be less than 3.9. All right, that's method 2. Method 3 says do the exact same thing, but when you get to here and you're trying to figure out whether you need a greater than or a less than sign, do a quick sketch. I'll do it over here where you can see it. Now, what I'm trying to do here is to actually sketch a rough sketch of y equals 2 to the power of x. Well, I know that's an exponential, it goes roughly like this, goes through 1 and goes shooting up. Now let's sketch y equals 15. Well, that's some horizontal line up here. Okay, it's not to scale, but if this is 15, it's a horizontal line. So we want the x values. We've found where these two meet, and solving this is a way of spotting the intersection, which must be 3.9 or so. And we're wondering, do we want the values up here or do we want the values down here? Well, we want the exponential graph, the curvy one, to be sitting lower or smaller than the straight line. Here's the straight line, here's the curvy exponential graph. We want the exponential graph to be lower, and that happens here for all the values of x, here and below. So that tells me that we take our 3.9 and we need all the values of x that are smaller than it. Now, is the graph essential? No, but this is a method that we can use for lots of other types of problems later, so it's handy to consider it now. Now, when we're solving inequations that have logs in them, it's handy to have those 3 methods that we just learnt with the indices ready at our disposal, because depending on where the x is, it can be tricky and we can easily get confused, and there's no really good rules of thumb to remember exactly which way to face the sign and how to move it around as we retell this log as an index expression. So to me, the method that makes the most sense is that method 2. Let's solve what we would do if it was an equal sign. Well, what I would do is I would retell this as an index expression and say 10 to the power of 4 is equal to x. So therefore x is, I can do this in my head, 10,000. All right, now what? Now we need to think about whether x needs to be greater than 10,000 or less than 10,000. Now we know that it needs to be greater than or equal to, so obviously we need that equal sign there. Now, to think this through, 10 to the power of 4, that's a big number, but this is the power that we want. We can easily get stuck, and here's where I think the graph for method 3 comes in handy. Now, in our next exercise, we're going to learn all about log graphs. At the moment, you've never seen a log graph, so it's hard because we're sort of learning something ahead of where you're about to need it. But a log graph looks something like this. Y equals the log with any base of x. So if I've got some log curve and I want to graph y equals that thing, and I'm also graphing y equals 4, I can get an easy conceptual understanding of what this looks like. I want to find the values of x where the curvy graph, the log graph, is greater than or equal to this horizontal line. So if I find the intersection point, which is actually what I've just found here, obviously my graph is nowhere near to scale, but that's fine. I can see that I'm going to want the part where my log graph is up higher than the horizontal line. So I need the values of x that are greater than 10,000. That helps me make my statement at the end like this. And I think using graphs in this way really helps us to prevent a mistake. The other thing you could do is use some trial and error. If you take the log with a base 10 of, say, 15,000, is it greater than 4? Because if it is, then that number that's bigger than 10,000 is in your range, and that will help you to see which way your sign needs to go.